Neuralink, merging humans and artificial intelligence. In 1985, the science fiction writer Bruce Sterling wrote of future worlds inhabited by two groups of humans. The shapers believed in altering their bodies using biotechnology and genetic engineering to achieve superhuman capabilities. The mechanists used mechanical and electronic alterations to gain the same brain-body advantages. It's safe to say that Sterling wasn't too far off the mark, at least for brain-related modifications. Nowadays, neuroscientists use both genetic and mechanical modifications to study as well as manipulate brain activity. But Elon Musk seems to prefer the mechanist's approach with his new venture Neuralink. Musk delivered a speech followed by a slew of announcements about the technologies Neuralink was working on towards building an advanced brain-machine interface, BMI, on July 16 in California. A BMI is a broad term for any communication pathway or device that allows humans and animals to translate their brain signals into commands that machines can execute. According to Musk's preprint paper, Neuralink's goal is to build a scalable high-bandwidth BMI system. Thus far, the company's scientists and engineers have replicated three cutting-edge inventions. The first is an ultra-thin electrode to be inserted inside a brain to relay electrical signals between the brain and a computer. The second is a robotic instrument to carefully implant the electrodes. The third is a small chipset to amplify and manipulate the signals. This technology, Musk said, may eventually help humans merge and communicate with an artificial intelligence AI. This is a grandiose claim that does little to counteract both the absence of important details in Neuralink's preprint paper and the fact that Neuralink has essentially repeated research that has already been conducted. In fact, there is a chasm between the contents of Neuralink's paper and the possibilities Musk presented in his speech. The road to these possibilities is long and hard, and not without problems. And even as the Neuralink paper is a relatively more detailed source of information than the televised announcement, it can still benefit from a good deal of unpacking in terms of important data that hasn't been shown and whether Neuralink's achievements are truly novel or game-changing. As in many other important things in our world, the devil or demon, a term Musk used to talk about AI in 2014, is in the details. It's very difficult to build a system in which all these components play well with brain tissue. Scientists have been working on ways to tap directly into brain activity since the 1920s. As a neuroscientist who studies electrical activity at the level of neurons, I find it fascinating to decode the activity of neuronal networks. But even with my limited familiarity with BMIs, some of Neuralink's pieces don't seem to fit the puzzle very well. 1. The problem of choosing a brain region. For starters, the Neuralink preprint paper doesn't mention anything about targeting a specific region of the brain. All it says is the electrodes will be implanted in the cerebral cortex. Why is this important? The cerebral cortex is a thin layer of neurons that covers almost the entire surface of the brains of mammals. It is roughly organized into major regions devoted to processing information from our primary senses: vision, hearing, taste, smell, and touch. BMIs are mostly used to help paralyzed people and amputees control robotic limbs and slash or move cursors on a screen. This requires scientists to implant electrodes into the sensoromotor regions of their cortex. 2. Pitfalls of electrode design. The cerebral cortex is organized like a 6-layer cake made of neurons. Each layer contains unique sets of neurons that modify incoming information and pass it on to neurons in other layers. To better understand this process, neuroscientists have defined a cortical column as a physical and anatomical unit of computation in the cortex. Imagine a cylindrical slice of the layer cake. Each such column contains a small sample of all the cells in all the layers of the cortex. To record information from cells at every layer of a cortical column, most electrodes are fabricated as long, thin needles with conducting points along their length. Each of these points is a recording channel that can eavesdrop on neuronal activity. Obviously, a larger number of electrodes and channels means that we can listen to more activity across swaths of the brain. Living brain tissue has the consistency of an almost liquid jelly. It doesn't flow, but it definitely deforms when you poke at it. So any foreign body, especially electrodes, cause microdamage and trigger the brain's immune system when inserted into this tissue. Cells known as glia grow and wrap around the electrodes, leading to a big decrease in the amount of signal detected over time. One way to overcome this problem is by making thinner and more flexible electrodes that cause less damage. But thinner electrodes also bend more when being inserted into jelly-like brain tissue and are more liable to break themselves. To solve this problem, Neuralink's robot can assemble and sew extremely thin electrodes, a few millionths of a meter wide, right into brain tissue. This solution, and the advance in BNI technology it engendered, is very similar to that achieved by a robot developed at the University of California's Berkeley and San Francisco campuses with DARPA funding, their preprint paper from March here. The people behind both robots claim the machines can avoid blood vessels thanks to onboard cameras and detection systems, minimizing damage and blood loss. 3. A chip with a chip on its shoulder. The electrodes are connected to a chip that is also implanted on the head. Its purpose is to receive signals from the electrodes, amplify them, and modify them into digital or analog signals, depending on whether the electrodes are reading or writing. Neuralink's chipset can stimulate and record from 1,536 or 3,072 channels, depending on the system. This beyond the current state-of-the-art in terms of the maximum number of channels from which one chipset can manage data. On the flip side, it is only connected to a USB-C connector, currently mounted on the test subject's head. This is curious considering wireless transmission of brain signals has been around since at least 2015, and physical wires could make things more cumbersome. 4. Are you human or rodent? Currently, Neuralink's machining techniques have been tested only with rats, where the BNI implant weighs 11 to 15 grams. How will this scale up to a human brain? A human brain and a rat brain don't just look different. They also contain different neurons, circuits, and regions. So it's important to ask how Neuralink plans to pick regions on a human brain, especially since we're still discovering new behaviors connected with specific regions in rodents, and are nowhere close to having a full-scale and precise map of region to function in a human brain. If you enjoyed this video and found it informative, make sure to hit the like button and subscribe to our channel for more engaging content like this. Thank you for watching.